Hello guys, nice to see you. Hi, how are you doing guys? Hello. Good afternoon. Yeah, thanks. Not bad. Quite. Doing quite well. So, I guess most people already have joined who wanted. Short recall of our previous discussion. We started kind of new topic, which is focused on waves. Um, So obviously, if we have some oscillator, then we can create in some medium wave which spreads in this medium with, so it can transfer energy. So we will talk about that a bit later, but it doesn't move in this direction of spreading the wave, the small elements of the medium. So they kind of oscillate around some equilibrium condition, either along the direction of the spreading of the wave that stands for longitudinal wave, and another option is when the small elements of the medium, they oscillate perpendicular direction to the spreading of the wave, which is another type of wave called transverse wave. And also we derive the wave function equation and introduce some parameters which quantify wave in terms of characteristics like period, also wavelengths, which stands, for instance, for distance between 2 points at like adjacent points at wave with the same phase, and the minimum distance between them is determined as the wavelength. It's one of the key parameters of all waves. So today we continue our discussion on waves, and our primarily point of interest for today will be discussion and derivation of equation which provides us a possibility to calculate the speed of waves which are spreading along a string. So also, I believe we will touch such topics as reflectance and transmittance of waves. So it will be more in general discussion to have basic understanding of these effects. But the primarily point of interest for today is this speed of wave spreading along a string. Okay, so let me switch to the slides. And let us start our discussion. Sorry. Let us consider such imaginary experiment in our efforts to understand how we address this question. What is the speed of spreading of a wave along a string? So when we, for instance, have some force which acts at the end of the string and pulled it some upwards or downwards, then it releases some tension on like inside this, like induces some tension inside this string. And if we consider a small element of a string, then this tension will cause some acceleration of this small element. So if we consider something like this, let's say we have a system of coordinates, x, y. Let us consider one pulse. This is our string with one pulse on it. So now we consider some small element of this string. Let us call it delta S. And the larger tension induced in the string because of external disturbance. The larger acceleration, this small element of the string will experience. So that means that the pulse or wave obviously can move faster, because if it accelerates faster, then this disturbance can spread along the string at a higher speed. Which another parameter do you believe is important in this consideration, which, for instance, would be reversely proportional? So the speed will be reversely proportional to this parameter. So we found this tension, obviously higher tension, high acceleration, it should definitely result in higher speed. Any ideas what else we should consider? Another very important parameter. Imagine you have but so acceleration and velocity have phase difference. Sure, they do have, but we need to understand from material properties some features which will define how fast some mechanical disturbance can move along this string. So imagine, so we agree that tension in the string is of great importance. Imagine that you have you seen maybe in gym, there is some exercise where people start to shake very thick ropes, quite thick and heavy ropes. So actually they create some mechanical waves, and that is quite energy consuming, so cannot continue doing that for long without proper training, so some fitness training. Imagine that you would have the same material but twice thinner, like twice smaller diameter of this rope. I believe that it would be much easier to create these waves, and also it is elastic potential energy. Well, that's kind of closer to the point. The thing is that if we consider, still come back to this small element, delta S. So, and we are initially talking about acceleration. So acceleration is defined as force divided by mass. And we know that in order to spread this mechanical disturbance faster, we need high acceleration of small elements of the string. That will be resulted from high, like large force, means large tension in the string. However, if this small element is heavier, you see we have this mass in the denominator. And if this small element gets heavier, then at the same force, we will get smaller acceleration, obviously. So at the same force, we get smaller acceleration, and it will result in smaller speed of spreading of this disturbance, mechanical disturbance along the string. So means if we consider that v is a velocity of spreading of our wave along the string, we mention, let's not put equal because we don't know exactly, but it should be proportional to the tension T inside this rope, and should be reversely proportional to the mass of each of these small elements. But then how we deal with this? It's convenient to operate with mu, which is linear density, like distribution of mass along unit of length of this rope. So mass of this small element would be then defined as delta S times mu. Since mass itself is not a parameter because it depends on how long element of this string we take, but mu is parameter of the string itself because it just defines from which material and what size, what is cross-section area of this string which we deal with. So that's why we can claim that it should be proportional to the tension and reversely proportional to this linear density. That's some suggestion. I believe you agree with this suggestion, kind of makes sense. And at the same time, it's not sufficient enough for us because we can only put some proportionality, but we cannot put equal. So we want to know the exact equation which will give us a chance to calculate accurately the speed of spreading of mechanical waves along strings. So now, in order to come to this quantitative part, let us consider this small element of the string in more details. So let us consider that like this particular area. So let us draw it here, kind of enlarge. So we will have some element of this string. Which will be with a length delta S. Then we need to consider what is moving and where. So let us assume that our pulse is moving from the left to the right. So in that case, if we consider some system of reference, which moves together with this pulse from left to the right with the same speed. So in that case, the element of the string will be considered moving with respect to our system of coordinates, which is mobile, this system of reference. Our element will move to the left, from right to the left, with the speed which is equal to v, speed of spreading the mechanical disturbance or this pulse. So why it happens? Because the element is actually immobile with respect to this stationary system of coordinate xy. Then if we consider it with respect to another system of coordinate which is mobile and moves together with the pulse with the same speed, then with respect to this mobile system of coordinates, it will move to the left with the speed of our pulse. So we can write here that it moves to the left with this speed v. Now, what we need to do next. Here is this small element forms a segment of a circle with a center in this, let's put point O. And this distance here will be radius of the curvature of this small element. Now, let us draw here a vertical line, and we can claim that this angle is theta. Now, if we have another horizontal line, then to the tangent of this curvature, this angle from horizontal to the tangent will also be equal theta. And the same from this side. So we will have some tension in this string, which is there, and we need to take it into account. So it will be tension T. And here also the same tension T. So now, when we have such a model, we can proceed further and consider what's actually going on. So since this element is kind of moving on a circular trajectory, it will possess some centripetal acceleration. So we can write that acceleration centripetal will be v squared divided by radius. So from other side, there are two vectors for tension from left side and from the right side. So they are equal, oriented at the same angle, means that in horizontal direction, they will compensate each other. So there will be no component in the horizontal direction. However, there will be some net force originated from these two tension vectors downwards. And that we can, so let's call it some radial force. Let's call it like this, F radial. So this radial force will be equal to 2. We have 2 of these vectors times t times sinus theta. And now, if we assume that angle theta is very small, so we don't create really huge pulses, but like small amplitude, don't go to extreme cases, then we remember that we can make approximation that sinus theta for small theta is equal to theta. So we can substitute this sinus theta with just theta. That will be 2 times t times theta. So with this radial force, we already figure things out. And we can be sure that it's in equilibrium. So there should be compensated this radial force by centripetal force. So in that case, we should write that Fr, which is equal to 2 times t times theta, should be equal to m times v squared divided by r. So now we have this m, and we need to define it somehow. And better that we define it in terms of theta in order to get rid of this angle in final equation. So we mentioned here already that mass is equal to delta S times mu. How can we express this length of the segment, delta S, in terms of theta?
Maybe theta divided by some angle, which is like a fraction of the circle, and multiplied by circumference.
Yeah, but we don't know circumference. We know radius, and if we know radius and angle theta in radians, then the length of the
length of the arc is like theta divided by 360 and multiplied by 2 PR. No?
That is equal to radius times theta. So it's definition of angle in of one, like of radians. So we know that 2 pi is full angle, 360 degrees in radians. And we also know that the circumference of the circle is 2 pi times radius. So you see that the length of the arc, like circumference of the circle, is equal to radius times angle in radians. And angle in radians, when we consider full angle, 360 degrees, is 2 pi. So that gives us the length of this arc if we know radius and angle theta. So we can now substitute instead of delta S, or this product radius times delta times theta, and that will be the following. So will be radius times theta times mu. So now we can substitute it instead of mass here in this equation. So it will be 2 times t times theta equal okay, there is one thing we missed, because theta is half of this angle on which the arc is residing. That's why we need to use 2 theta. So here should be 2. 2 theta times r will give us the length of this segment. If we multiply only by theta, it will give us length only of this part of the arc. So we need 2 theta. So it will be then 2 times r times theta times mu times v squared and divide by r. Okay, so let's see what we get here. Radius cancel out. Theta and theta cancel out. 2 cancel out. So therefore, from this equation, we get that speed of spreading of a mechanical wave along a string is equal to a square root of tension divided by linear density mu. So that is the explicit form of the equation, which gives us the speed of mechanical waves in along strings. So you see that we are not so far from our initial prediction. Actually, indeed, these two parameters define how fast mechanical waves will move along the string. However, definitely we could not predict this square root. That's why we had to go for analytical derivation of this equation.
Excuse me.
Yes.
How is it called again? Like velocity of propagation of wave or what?
Along a string, yeah.
It's like along the string or along x-axis, or is it like the same?
It's along. Well, the thing is that technically, since we assume this theta quite small, it is along the string and along axis x. But the thing is that we consider how fast this mechanical disturbance, like pulse, for instance, can move when we create it in a string. So let's consider we have some direction of propagation of spreading this mechanical wave or pulse, and that defines how fast this pulse can move along this direction. And that is also along the string, because that's in which direction the string is stretched.
Okay.
Because we need tension. It should be stretched. Otherwise, we don't have tension. Tension is equal to 0. Then wave cannot spread because velocity will be the speed will be equal to 0. So we consider the pulse itself, which moves along axis X. Okay, so now we can proceed further and consider some important general statements about reflectance and transmittance of mechanical waves. So let me share my screen. One second. Okay, so now let us assume that we created some pulse in a string which is attached to the wall. So it is firmly fixed, cannot move this end. And this pulse is moving from the left to the right, hits the wall. In the moment when it reaches the wall, there is some upward force acting on the wall from the side of the rope as this pulse is coming. And according to the third law of motion, we have some counter force which acts downwards from the side of the wall on the string. And that results in a reflected pulse. However, in this case, it will be flipped over. So if we had, let's say, some positive amplitude, then we have negative displacement of these elements of the string. So what actually happens if we neglect with any dissipation of energy at this interface, we will have the same pulse reflected from this wall. However, it will be in opposite phase. So there will be a phase shift between the incident and reflected pulse. So another option when we have some freely moving end of this rope. So let's say it's attached to some light ring at the end. So we create this pulse which moves to the right, and then we this pulse reaches the end of the rope, creates some upward force on the ring. Since it's light, it's not fixed this end as in previous example. There is no counter force, it just goes up, reaches the amplitude value of displacement of this pulse, and then goes down. So in this case, there is no this counter force, reaction force, and our reflected pulse, which also goes in the opposite direction, remains in the same phase as the incident pulse. So that highlights the features of reflecting mechanical waves. However, there is another effect, and usually they happen simultaneously. So there is also transmission. So now let us consider a system of two strings. One is thinner, another thicker, means one has smaller linear density, another thicker linear density. If we create a pulse in a thinner string, it moves to the interface between these two strings. And at the interface, when our initial incident pulse moving from the side of thin string. Reflected is moving backwards in the thin string with opposite phase, similar to this case when we have firmly fixed end of the row. And there is some energy of this incident pulse, which is transferring to another row, which is thicker. And in that case, we have transmitted pulse in the same phase as the incident. However, pay attention. Here we have larger amplitude, and here we have smaller amplitude. Obviously, energy of this pulse, assuming that we don't have any losses, has split it in two components. So we have one component which is reflected with different phase, and another transmitted in the same phase. So we split energy in reflected and transmitted. Another thing what should be taken into account is case when we have incident pulse originally created in this heavier string. So means in the medium where speed of spreading this pulse is lower in comparison to the other medium, which is attached at some point to each other. So in this case, we also have reflected and transmitted pulses. However, it behaves more like in this example when we have freely fixed end of the string, and at the interface we get reflected pulse in the same phase, which moves backwards along this dense row, and also we have transmitted pulse in the same phase in the thinner row. So that is important to keep in mind, because when we deal with reflectance, so transmittance is kind of simple. So in both cases, we have the same phase of transmitted pulse. However, we need to keep in mind at interface of which mediums this reflectance is happening. Because if pulse is moving through the first medium with a higher speed of propagation, then reflected wave or reflected pulse will be in opposite phase. That is important because, for instance, if we consider some cases of interference between incident and reflected mechanical waves, like their interaction. So their interaction will be different based on the phase of reflected pulse or wave. That's why you need to keep in mind from which side of the interface reflectance is happening, and take this phase shift into account. So summarizing, I would like to mention that today we discussed the speed of spreading wave along string. We assumed at the beginning that it should be proportional to the tension in the string, and also reversely proportional to the linear density of the string, means the weight of the single or some unit length of the string. The heavier unit length of the string, the smaller speed of propagation of this mechanical wave. So we calculated, derived this equation based on analytical calculations, and we got the equation, which is square root of tension divided by mu, which is linear density. So that it was quite accurate prediction, and indeed these parameters are the key parameters to define the speed of mechanical waves in strings. However, we need to highlight that in our calculations, we assume that this angle theta means the amplitude of the pulse should be quite small, where in this range when we can substitute sinus theta with theta without much of the error. And also we considered the reflection and transmittance of mechanical waves from interface between different strings with higher and lower linear densities, depending on the direction, depending on the side from which the incident pulse approaches the interface between these two ropes. We need to consider either we have some phase shift in the reflected wave, or we don't. So if the pulse approaches from the lighter and thinner string, then we do have phase shift, like opposite phase of the reflected wave. And if in the contrary, when some pulse is approaching the interface from the side of denser or thicker string, we don't have this phase shift with the reflected pulse. So that is important to keep in mind. And on our next discussion, we will continue with waves. In particular, we will consider the transfer of energy with wave and do accurate, like, analytical derivation of equation, how much energy per unit time mechanical wave can transfer through some medium, and which parameters will have an impact on these features of mechanical waves to transfer energy. Okay, thank you for attention. If you have any questions, you're welcome. So if everything was clear, then we meet next time on Friday. Take care, have a good day, and see you on our next discussion. Bye-bye.
Thank you. Goodbye.
Bye-bye.